The history of precision optics is the chronicle of humanity's quest to manipulate the fundamental properties of light. What began as the accidental discovery of magnification through natural crystals has evolved into a highly precise, mathematically governed discipline capable of manipulating individual photons and etching nanoscale patterns onto semiconductor wafers. This evolution rests upon a tripartite foundation: the discovery and refinement of material science, the formulation of theoretical physics, and the relentless advancement of manufacturing techniques. By tracing the chronological development of optics, a profound narrative emerges regarding how light manipulation has shaped human progress.
In the ancient world, the manipulation of light was an empirical phenomenon divorced from mathematical understanding. While Egyptian hieroglyphs and early Bronze Age finds suggest that rudimentary lenses were utilized in ancient Egypt and Greece, the most prominent physical artifact from this era is the Nimrud lens, also known as the layered lens. Unearthed in 1850 by Austin Henry Layard in the ruins of the Assyrian palace of Nimrud in modern-day Iraq, this artifact dates back to the 8th century BCE. The slightly oval piece of rock crystal measures 38 millimeters in diameter and was roughly ground, likely on a lapidary wheel, to possess one flat and one slightly convex face. With a focal length of approximately 12 centimeters, the Nimrud lens functions as a crude 3-power magnifying glass.
The primary use of the Nimrud lens remains a subject of intense scholarly debate. While some opticians argue it was deliberately manufactured as a magnifying optical tool or a burning glass to start fires by concentrating sunlight, other historians contend that its optical properties are purely accidental. Layard noted that the crystal was found buried beneath a heap of decayed blue opaque glass enamel, and the surface of the lens features 12 cavities that once contained naphtha trapped in the raw crystal. This context heavily suggests it was utilized as a piece of decorative inlay for wooden or ivory furniture. Regardless of its intended purpose, the artifact demonstrates that the material science required to grind and polish quartz existed millennia before the theoretical frameworks required to understand optical refraction.
During the Greco-Roman period, empirical observations of light manipulation continued to outpace theoretical physics. The Roman philosopher Seneca the Younger noted that reading through a glass globe filled with water magnified the text beneath it. He famously claimed to have read all the books in Rome using this method. However, the foundational misunderstanding of this era was attributing the magnification solely to the water rather than the curvature of the glass medium. Because the precise geometric interface between air, glass, and water was not mathematically understood, these observations did not translate into the widespread manufacturing of practical optical lenses. Concurrently, classical theories of vision actively hindered the development of optics. Prominent mathematicians such as Euclid and Ptolemy subscribed to the extromission or emission theory of vision. This philosophical stance posited that the human eye emitted active rays of invisible light to illuminate and perceive the surrounding world. This theory positioned light as a product of human biology rather than an independent physical phenomenon, thereby delaying the study of light as a manipulable external force. The critical theoretical breakthrough that laid the groundwork for modern optical physics occurred during the Islamic Golden Age, driven by the Arab polymath Abu Ali al-Hasan ibn al-Haytham, known in the West as Alhazen. Born in 965 CE in Basra, Alhazen rejected the classical extromission theories and proposed the modern intromission theory of vision, asserting that vision occurs when light reflects off external objects and subsequently enters the eye. His seminal 7-volume treatise, The Book of Optics, Kitab al-Manazir, published between 1011 and 21 while he was under house arrest in Cairo, fundamentally shifted the study of light. Alhazen utilized the camera obscura to empirically prove that light travels in straight lines and that images can be projected through a small aperture, laying the foundation for his geometrical studies of refraction and reflection.
Beyond his specific discoveries, Alhazen's most profound contribution was his rigorous application of the scientific method. He insisted that theoretical claims must be verified through physical experimentation, stating that to learn the truth, a scientist must become the enemy of all that he reads. By proving that light is governed by physical geometries rather than human emission, Alhazen transformed optics from a branch of philosophy into a quantitative physical science.
Despite Alhazen's theoretical advancements, the practical application of optics remained relatively stagnant until the High Middle Ages. In 10th century Europe, monks working in scriptoriums began utilizing reading stones to assist with their illuminated calligraphy. These were hemispherical domes of polished, transparent quartz laid flat against manuscripts to magnify the text. While highly effective for individuals with presbyopia, these stones were cumbersome and restricted to the literate elite. The transformative leap occurred in Italy in the late 13th century, between 1268 and 1300, with the invention of the first wearable spectacles. While popular myths sometimes credit a Florentine named Salvino d'Armati with the invention, scholars have largely debunked his existence, leaving the true inventor anonymous.
Craftsmen achieved this breakthrough by placing two convex magnifying lenses into rigid frames connected by a hinge that rested delicately on the bridge of the nose, creating the first hands-free vision correction devices. Initially, these early spectacles were manufactured from expensive rock crystal, cementing them as luxury status symbols for the wealthy. However, the invention of the printing press in 1440 caused a massive global surge in literacy rates, which subsequently drove an unprecedented demand for affordable reading glasses, necessitating a shift from natural quartz to manufactured glass.
The widespread adoption of optical instruments required a revolution in material science, which was catalyzed by the glass-making guilds of Venice, particularly those concentrated on the island of Murano. Relocated to Murano in 1291 by Venetian law to prevent urban fires and to fiercely guard their proprietary recipes, these craftsmen held a strict monopoly over European luxury glass production. The primary hurdle in medieval glassmaking was the presence of iron impurities, which gave standard glass a murky green tint that obscured vision and limited light transmission. In the 15th century, Murano glassmakers achieved a monumental breakthrough with the invention of cristallo, an almost perfectly transparent glass that rivaled the optical clarity of natural rock crystal. The manufacturing technique required a highly refined transcultural supply chain. The glassmakers utilized crushed white quartz pebbles, known as cogoli, sourced from the Ticino and Po rivers to provide highly pure silica. To lower the extreme melting point of the silica, they utilized allume catino, an alkali flux derived from the calcined ashes of salt-tolerant Ushnan plants harvested by Bedouins in the eastern Mediterranean. Crucially, they introduced pyrolusite, a manganese-based glassmaker soap, which chemically oxidized the iron impurities during the melt, leaving the resulting glass colorless. This pristine transparency was the absolute prerequisite for the future of optics. Clear cristallo glass enabled the production of reliable chemical vessels, allowing chemists to monitor reactions and isolate pure materials like mineral acids and alcohol, which fed back into broader scientific and medical advancement. Furthermore, the optical purity of Murano glass allowed lens grinders to shape uniform, predictable optical components free of internal distortion, setting the physical stage for the scientific revolution. The late 16th and early 17th centuries witnessed the convergence of Murano's advanced glassmaking capabilities with Alhazen's geometrical optics, resulting in the invention of the first compound optical instruments. In the Netherlands, instrument makers such as Zacharias Janssen and Hans Lippershey experimented with combining multiple lenses within a single tube. They independently contested the inventions of the first compound microscopes around 1595 and the first refracting telescopes around 1608.
These early, crude instruments utilized a convex objective lens and a concave eyepiece, providing modest magnification, but suffering from severe image distortion and a remarkably narrow field of view. When news of the Dutch perspective glass reached Italy, Galileo Galilei immediately set about improving the manufacturing techniques. By grinding his own lenses to higher tolerances, Galileo constructed a telescope capable of astronomical observation, utilizing the traditional Galilean design of a convex objective and a concave eyepiece. This design provided an upright image, but because much of the light collected by the objective was lost before entering the eye, it severely limited the field of view.
In 1611, the German astronomer and mathematician Johannes Kepler published Dioptricee, fundamentally redesigning the telescope based on the theoretical physics of light. Kepler proposed a system utilizing two convex lenses. While this Keplerian design inverted the resulting image, rendering the world upside down, it ensured that all light collected by the objective entered the eye, dramatically increasing the field of view, improving image illumination, and allowing for much higher magnification powers. For astronomical purposes, the inverted image was irrelevant, and the Keplerian telescope quickly became the standard for celestial observation. As optical instruments grew more powerful, they revealed a persistent manufacturing flaw: chromatic aberration.
Lenses essentially function as prisms, and because different wavelengths of light bend at slightly different angles, early telescopes could not focus all colors to a single point. This optical geometry resulted in stars appearing with distracting red or blue halos, severely limiting scientific observation.
Isaac Newton approached this problem through the lens of his corpuscular theory, which posited that light consisted of discrete physical particles. Newton demonstrated via prism experiments in 1672 that white light is a heterogeneous mixture of refrangible colors, arguing that color is an intrinsic property of light. Believing that chromatic aberration was an inherent, irremediable defect of all refracting glass, Newton abandoned lenses entirely and invented the reflecting telescope, utilizing a concave parabolic mirror to focus light without color dispersion.
Conversely, the Dutch polymath Christiaan Huygens formulated the wave theory of light in 1678, proposing that light propagates as a series of elementary spherical waves. Huygens utilized his wave principle to explain complex optical phenomena such as refraction, the lower speed of light in dense mediums, and the polarization observed in birefringent crystals. By applying his theoretical framework to optical design, Huygens developed advanced multi-lens eyepieces that partially corrected for spherical and chromatic aberrations in refracting telescopes, proving that glass optics still held massive, untapped potential. While astronomers looked to the heavens, the Dutch draper and self-taught microbiologist Antonie van Leeuwenhoek turned his attention to the microscopic world. Recognizing the severe aberrations and technical difficulties inherent in manufacturing the tiny compound lenses for early microscopes, Leeuwenhoek abandoned the multi-lens system entirely. Instead, he pioneered a proprietary manufacturing technique that bypassed the traditional, laborious process of lens grinding.
By carefully melting small glass rods in a flame, Leeuwenhoek created perfectly spherical glass beads. These tiny biconvex ball lenses possessed incredibly short focal lengths, but offered unprecedented magnifying power, achieving magnifications ranging from 275x to over 300x without the compounding chromatic errors of multi-lens systems. He mounted these single lenses between two flat, riveted brass or silver plates, equipped with highly precise positioning screws to manipulate the specimen's distance and height relative to the lens. This masterful convergence of simplified optics and precise mechanical staging allowed Leeuwenhoek to become the first human to observe single-celled organisms, bacteria, and spermatozoa, fundamentally establishing the field of microbiology.
The 18th century shattered Newton's assumption that chromatic aberration in glass was an unsolvable absolute. The breakthrough relied on an advancement in materials science, the recognition that different chemical compositions of glass possess different dispersive properties. English lawyer and amateur optician Chester Moore Hall recognized this principle in the 1730s by experimenting with different glass combinations. But it was the English optician John Dolland who successfully commercialized and patented the achromatic lens in 1758. Dolland engineered an achromatic doublet by nesting a convex lens made of crown glass against a concave lens made of flint glass. Crown glass, manufactured with alkali lime silicates and potassium oxide, possesses a relatively low refractive index and low color dispersion.
Flint glass, which was revolutionized in the 1660s by George Ravenscroft's introduction of lead oxide to the glass composition, possesses a much higher density and higher dispersion of the glass. By combining these two distinct materials, the color dispersion caused by the crown glass was exactly canceled out by the opposite dispersion of the flint glass, effectively bringing multiple wavelengths of light to a single focal point without distortion. This combinatorial manufacturing technique rescued the refracting telescope from obsolescence. In the early 19th century, the German physicist and master glassmaker Joseph von Fraunhofer elevated optics from empirical craftsmanship to an exact mathematical science. Fraunhofer recognized that to calculate the perfect achromatic doublet, one needed a highly precise method to measure the specific refractive indices of optical glasses across different colors of light. In 1814, while passing solar light through a thin slit in a prism, Fraunhofer noticed and systematically mapped over 570 dark absorption lines in the solar spectrum, which are now universally known as Fraunhofer lines. These lines, caused by the absorption of specific wavelengths of light by chemical elements in the sun's atmosphere, provided absolute, unchanging wavelength standards for optical measurement. Furthermore, Fraunhofer invented the diffraction grating in 1821, utilizing 260 closely spaced parallel wires to accurately measure the precise physical wavelength of these specific colors and dark lines. By using these exact mathematical measurements, Fraunhofer could formulate optical glass and design objective lenses with a level of precision entirely divorced from the trial and error methods of his predecessors, effectively laying the foundation for stellar spectroscopy and modern optical engineering.
The ultimate industrial shift in precision optics occurred in the mid to late 19th century in Jena, Germany, through an unprecedented collaboration between three men: the mechanic Carl Zeiss, the physicist Ernst Abbe, and the glass chemist Otto Schott. This partnership represents the moment optics became a fully integrated modern industry.
In 1846, Carl Zeiss opened a workshop producing simple microscopes, but found that the traditional method of trial and error grinding had reached its physical limits, preventing further increases in image resolution. To solve this bottleneck, Zeiss recruited Ernst Abbe, a brilliant physicist at the University of Jena. Abbe fundamentally transformed microscope design by creating its rigorous mathematical foundation. In 1873, he formulated the Abbe sign condition and defined the diffraction limit of optical resolution. Abbe proved mathematically that resolution is restricted not by manufacturing flaws, but by the physical wavelength of the light and the numerical aperture of the lens, expressed in a formula involving the refractive index and the sine of the aperture angle.
However, Abbe's theoretical designs required glass with highly specific refractive and dispersive properties that simply did not exist in the traditional crown and flint repertoire, severely limiting physical implementation. To bridge this gap, Zeiss and Abbe partnered with the young chemist Otto Schott in 1884 to found the Schott & Associates Glass Technology Laboratory. Schott systematically developed revolutionary new glass chemistries to meet Abbe's specific numerical demands, including lithium-based glass, barium crown glass, and highly durable borosilicate glass. Schott's material science provided the exact optical parameters dictated by Abbe's mathematics, allowing the Zeiss firm to manufacture the first true apochromatic lenses. These advanced lenses completely eliminated color distortion and brought optical resolution to its absolute physical limits, forever changing the global optical industry and establishing the modern paradigm of mathematically dictated lens design. As optical instruments evolved in the 20th century to incorporate complex, multi-lens systems, a severe new physical problem emerged: reflection loss. Every time light transitions the boundary between air and a glass surface, between 4 and 8% of the light is reflected backwards due to the change in refractive index. In a complex optical system containing numerous lenses, cumulative reflection could result in the loss of over 50% of the incident light, resulting in incredibly dim images and severe glare.
In 1935, Alexander Smekula, a Ukrainian physicist heading the crystal laboratory at Carl Zeiss, solved this issue by inventing the first interference-based anti-reflective coatings. Smekula's manufacturing technique involved vapor depositing extremely thin layers of selected materials onto the glass surface within a high vacuum chamber. By precisely controlling the thickness of these nanometer-scale layers, Smekula engineered destructive interference for the reflected light waves and constructive interference for the transmitted light waves. This multi-layer technology, famously commercialized as the Zeiss T-star coating, virtually eliminated reflections and vastly increased light transmission, allowing for the development of highly complex, incredibly bright multi-lens camera, binocular, and rifle scope systems.
Concurrently, theoretical physics underwent a quantum revolution that redefined the fundamental nature of light itself. In 1905, Albert Einstein proposed that light does not behave solely as a continuous classical wave, but rather exists as tiny, quantized packets of energy called photons. Einstein used this concept to explain the photoelectric effect, demonstrating that electrons are only ejected from a metal surface if the incident photons possess a specific threshold frequency, regardless of the light's overall intensity.
Furthermore, in 1917, Einstein published a seminal paper on the quantum theory of radiation, wherein he mathematically predicted the phenomenon of stimulated emission. He posited that an incoming photon could interact with an excited atom, stimulating it to drop to a lower energy state and emit a second photon identical in phase, frequency, and direction to the first. This theoretical realization laid the direct groundwork for the invention of the maser and the laser decades later, ushering in the modern era of quantum optics.
The practical application of stimulated emission allowed for the generation of coherent laser light, first achieved by Theodore Maiman in 1960. This invention subsequently revolutionized global telecommunications through the development of fiber optics. Early attempts to transmit data through glass fibers in the mid-20th century were stymied by massive signal attenuation. Light scattered and absorbed so rapidly that transmission was practically limited to mere meters. In the 1960s, the electrical engineer Charles Cow engineered a monumental breakthrough in material science. He realized that the extreme signal loss was not an inherent physical limitation of glass itself, but rather the result of microscopic impurities scattered within the material. Cow posited that by purifying the glass to extreme levies, bundles of thin fibers could carry immense amounts of data over vast distances with minimal attenuation. By shifting from traditional optical glasses to highly purified fused silica, silicon dioxide, drawn into thin fibers with high index cores and lower index claddings, manufacturers achieved light guidance via total internal reflection with astonishing efficiency.
This manufacturing triumph dropped attenuation losses to an operational minimum of about 0.5 decibels per kilometer, completely replacing copper wires and laying the physical, high-speed optical foundation for the global internet. In the latter half of the 20th century, precision optics escaped the Earth's atmosphere entirely to bypass the blurring effects of atmospheric turbulence.
The pinnacle of this era was the launch of the Hubble Space Telescope in 1990. However, shortly after deployment, engineers discovered a catastrophic manufacturing error. The primary mirror suffered from severe spherical aberration.
A rigorous investigation revealed that a null corrector device, used to measure the mirror's curvature during the final polishing process, had been assembled with a 1.3 millimeter lens spacing error. Consequently, the primary mirror was polished too flat near its outer edges, by a fraction of a hair's width, causing incoming light to focus at multiple points and severely blurring the telescope's images.
Rather than abandoning the multi-billion-dollar observatory, NASA executed a masterclass in optical correction. During a historic 1993 servicing mission, astronauts installed the Wide Field and Planetary Camera 2, WFPC-2, which contained internal optics designed specifically to counteract the primary mirror's flaw. Additionally, they installed COSTAR, Corrective Optics Space Telescope Axial Replacement, a highly complex module roughly the size of a large refrigerator. COSTAR utilized deployable mechanical arms to place highly customized curved mirrors directly into the optical paths of the remaining scientific instruments, acting exactly like corrective spectacles for the observatory and restoring its vision to perfect clarity.
This era also saw the maturation of active and adaptive optics for massive ground-based telescopes. While active optics work on longer timescales to continuously adjust the primary mirror geometry to counteract mechanical and thermal deformation, adaptive optics, first envisioned conceptually by Horace Babcock in 1953, utilize high-speed deformable mirrors and wavefront sensors to counteract real-time atmospheric distortion, allowing ground-based observatories to achieve resolution exceeding previous atmospheric limits.
In the 21st century, the most extreme application of precision optics shifted from observing the cosmos to the manufacturing of nanoscale semiconductors. To continue Moore's law and print microchip features below the 5-nanometer node, the Dutch company ASML developed extreme ultraviolet lithography. This process utilizes light with a wavelength of just 13.5 nanometers, bordering on the X-ray spectrum, generated by firing high-power lasers at microscopic droplets of liquid tin traveling at high speeds within a vacuum chamber.
Because 13.5 nanometer light is entirely absorbed by almost all matter, including air and traditional glass lenses, ASML had to completely abandon transmissive optics. Instead, EUV systems utilize a series of massive Bragg reflectors to guide and focus the light. These optical mirrors rely on interference rather than standard reflection. They are manufactured by vapor depositing over 100 alternating atomic scale layers of molybdenum and silicon onto a glass substrate. To prevent imaging errors at such extreme wavelengths, these mirrors require unprecedented manufacturing precision, polished to an atomic-level smoothness measured in tens of picometers.
To illustrate this scale, if an EUV mirror were scaled up to the size of Germany, the highest topological anomaly on its surface would measure barely a millimeter in height. Furthermore, because the intense light pulses cause the optical system to warm up and distort by mere nanometers, the system utilizes thousands of actuators to actively adjust the orientation of the mirror elements, compensating for thermal expansion and ensuring a perfect image.
Astronomical optics have concurrently shifted toward ultra-lightweight, cryogenically stable materials and distributed observation networks. The James Webb Space Telescope, JWST, launched to observe the faint infrared light stretched by the expansion of the universe from the earliest galaxies, abandoned heavy, single monolithic glass mirrors. Instead, JWST features 21 primary mirror segments manufactured from beryllium, chosen for its extreme stiffness-to-weight ratio and ability to maintain precise dimensions at deep space cryogenic temperatures. These hexagonal beryllium panels are coated in a microscopic layer of gold to maximize infrared reflection and are aligned in deep space using nanoscale actuators.
Looking toward the future of astrophysical observation, the Laser Interferometer Space Antenna mission represents the pinnacle of space-based precision interferometry. Designed to detect the minuscule ripples in the fabric of space-time caused by gravitational waves from merging supermassive black holes, LISA will consist of 3 spacecraft flying in an equilateral triangle formation separated by 2.5 million kilometers.
Operating without physical mirrors stretching between the craft due to the immense distances involved, LISA relies on free-falling gold-platinum test masses and highly stabilized laser interferometry with critically elevated facilities. This requires optical bench architectures made from ultra-low expansion glass ceramics, such as Zerador, that can maintain path length stability down to picometer precision, completely isolated from solar radiation and mechanical drag.
The ultimate trajectory of optics in the 21st century is the departure from bulk glass entirely. For centuries, optical engineering has been strictly constrained by the physical necessity of curved glass to refract light to a focal point. Today, researchers in quantum photonics and material science are replacing macroscopic curvature with sub-wavelength nanostructures, creating a revolutionary class of flat optics known as meta-lenses. Meta-lenses are planar, ultra-thin surfaces populated by millions of precisely engineered microscopic pillars made from high-index materials like titanium dioxide or optimized UV-grade silica. By altering the physical geometry, diameter, and rotation of these individual nanopillars, engineers apply Huygens Fresnel principles to manipulate the effective refractive index of the surface. This allows the meta-lens to impart customized phase, amplitude, and polarization shifts to the incident light at a sub-wavelength scale without utilizing physical curvature. This mechanism allows a completely flat surface to focus multiple wavelengths of light simultaneously to a single point, achieving achromatic, diffraction-limited focusing while entirely avoiding the bulk, weight, chromatic aberration, and complexity of traditional multi-lens stacks. By applying external stimuli, these structures can even become reconfigurable, changing their optical properties on demand.
Furthermore, the manufacturing of meta-lenses bridges the gap between the optical and semiconductor industries. Rather than relying on the traditional, centuries-old methods of mechanical grinding and polishing, meta-lenses are fabricated using deep ultraviolet DUV projection lithography and electron beam etching. This enables the mass production of optical components directly onto semiconductor chips at scale. This paradigm shift promises to drastically miniaturize optical devices, replacing bulky lenses across machine vision, infrared thermal imaging, compact medical endoscopes, and wearable virtual reality headsets. Ultimately, the history of precision optics is characterized by a continuous, relentless feedback loop between theoretical abstraction and physical manufacturing. The journey from the crude grinding of the Assyrian Nimrud lens to the lithographic printing of sub-wavelength metamaterials illustrates a profound epistemological shift. Light is no longer a mysterious phenomenon to be passively observed through haphazardly polished crystals, nor is it a biological emission from the human eye. It is a highly defined physical entity to be mathematically modeled, quantized, and engineered. By conquering the chemical limitations of glass, mastering the quantum behaviors of photons, and engineering surfaces at the atomic level, the discipline of optics has not merely expanded human vision, it has continually redefined the limits of scientific possibility, shaping our fundamental understanding of everything from the biological microcosm to the cosmological macrocosm.